Good day. I am Dr. Suresh.S, Assistant Professor at the Department of Biotechnology, SRM Institute of Science and Technology, Ramapuram, Chennai. I am presenting at the International Conference on Emerging Trends in Healthcare Sciences 2025. My topic is ultrasound-assisted phytase production and its nutritional impact on cardiovascular health. Cardiovascular disease, or CVD, is a general term encompassing conditions that affect the heart or blood vessels. These diseases are typically associated with the buildup of fatty deposits, known as atherosclerosis, inside the arteries, which increases the risk of blood clots. CVDs include serious conditions such as coronary artery disease, hypertension, stroke, and heart failure. Major risk factors for developing these conditions include a poor diet, high cholesterol, diabetes, obesity, oxidative stress, and mineral imbalance. Preventive strategies must therefore focus strongly on nutrition, lifestyle changes, and metabolic regulation. Globally, cardiovascular disease holds the alarming title of the world's #1 killer. Statistics show that 20.5 million deaths occur every year due to CVD. This accounts for 33% of all global deaths. Crucially, more than 75% of these CVD deaths take place in low- and middle-income countries. Our study centers on the enzyme phytase. Phytase is critical because it catalyzes the degradation of phytic acid into myo-inositol phosphate derivatives, minerals, and various biomolecules. As seen in the figure, this reaction is vital for releasing crucial metal ions such as calcium, iron, and zinc, which are otherwise tightly bound by the phytic acid molecule. While traditionally seen as an antinutrient due to its mineral binding capacity, phytic acid and its breakdown products have various protective roles. Regarding cardiovascular health, it is linked to preventing vascular calcification and reducing the red cell distribution. Furthermore, its effects include antimicrobial activity against bacteria like E. coli and Bacillus subtilis, anti-cancer properties, prevention of urolithiasis by stopping calcium and oxalate crystallization, and benefits related to Alzheimer's and Parkinson's diseases. For diabetes mellitus type 2, phytic acid shows hypolipidemic and hypoglycemic effects. The consumption of phytase or its hydrolysis byproducts provides several mechanistic links to reducing CVD risk. Firstly, the improved mineral metabolism, specifically adequate magnesium and calcium absorption, helps reduce hypertension. Secondly, phytase hydrolysis byproducts may lower lipid levels, aiding in cholesterol metabolism. Thirdly, we see an antioxidant effect through reduced oxidative stress. Finally, phytase aids in gut microbiome modulation, which improves overall metabolic health and digestion. To enhance the effectiveness of phytase, we employed ultrasonication as a pretreatment step for rice bran. We used a titanium probe-type sonolyzer to facilitate the removal of lignocellulose from the rice bran. The next critical step was fermentation. We selected the fungus Rhizopus oligosporus for this purpose. Our oligosporus was chosen because it is generally regarded as safe, exhibits rapid growth, is non-toxic towards fermentative products and animals, and is widely known for its use in producing tempeh, a traditional Indonesian soy food. We fermented the pretreated rice bran using this selected microorganism. Our quantitative analysis measured fungal biomass, protein content using Lowry's method, reducing sugar via the dinitrosalicylic method, and phytic acid content. Results for fungal biomass, protein, phytic acid, and reducing sugar were expressed in milligrams per gram of dry substrate, or mg per GDS. For characterization, we utilized scanning electron microscopy and HPLC. To ensure a highly active and pure enzyme, we carried out a 3-step purification process: ammonium sulfate precipitation, ion exchange chromatography using the Cephros Cl6b, and finally, gel permeation chromatography with Cefacryl S200. Before treatment, the untreated rice bran contained 28.36 mg per GDS of phytic acid. Our results, shown in Table 3.1, demonstrated how various ultrasonic parameters, such as time, cycle percentage, liquid-to-solid ratio, and amplitude, affected the phytic acid content in both the treated rice bran and after subsequent fermentation. Optimization showed that at 40 minutes of ultrasonication time, the fermented rice bran reduced phytic acid content significantly to 8.0 mg. The scanning electron microscopy images visually confirm the impact of our methods. Figure 3.1 compares the texture of untreated rice bran with the structure of ultrasonic irradiated rice bran, demonstrating how the pretreatment physically alters the substrate to improve accessibility for the fermenting microorganism. Figure 3.2 illustrates the optimization of phytase production. Through these studies, we identified the optimal pretreatment time, cycle percentage, liquid-to-solid ratio, and amplitude for ultrasonic irradiation to ensure the highest yield of phytase enzyme activity using our oligosporus. The purification process was highly successful. Starting with a crude extract activity of 13.07 units per milligram, the final step, gel permeation chromatography using Cefacryl S200 resulted in a substantial purification. We achieved a 14.6 purification fold, with the specific activity increasing to 191 units per milligram. We tested the efficacy of the purified phytase. Figure 3.3 shows the release of inorganic phosphorus from soybean meal under acidic conditions, confirming that the enzyme is active in conditions mimicking digestion. Furthermore, HPLC chromatograms confirmed the effective breakdown of phytic acid. Panel A shows the initial phytic acid peaks, while panel B shows the result after phytase treatment, indicating successful enzymatic hydrolysis. We also studied how various minerals affect the activity of the purified phytase. The enzyme showed the highest activity in the presence of Mg2+, 167 units per milliliter, and Zn2+, 162 units per milliliter, suggesting these are important cofactors. Conversely, Cu2+ significantly reduced activity at 55 units per milliliter. Finally, we examined the in vitro dephytinization capacity of the enzyme across 5 different food grains: wheat, rice, corn, soybean, and rapeseed flours. The figures show that the phytase successfully reduced phytic acid content in all tested flours. Critically, this reduction corresponded to a significant enhancement in the release of inorganic phosphorus, soluble proteins, and reducing sugars, thereby improving nutrient bioavailability. In summary, our research achieved several key outcomes. Ultrasonic pretreatment enhanced phytase production from rice bran, leading to a remarkable 9.3-fold increase in enzyme activity. The purified phytase effectively reduced phytic acid in various flours, thereby improving nutrient bioavailability. We observed a significant enhancement in the release of inorganic phosphorus, soluble proteins, and reducing sugars. This improvement in nutrition enhances mineral absorption Ca2+, Mg2+, and Zn2+, which helps regulate blood pressure, lipid metabolism, and oxidative stress. Ultimately, the nutritional benefits enabled by this enhanced phytase production contribute significantly to lowering the risk factors associated with cardiovascular diseases. Thank you for your attention. Hope you all enjoyed the presentation.